This is slide number 73 and I am your presenter Asloob Mudassar. Types of holograms. A large number of different types of holograms exist which can be classified into one of the following categories: transmission hologram, reflection hologram, thin holograms, thick holograms, Fresnel holograms, Fraunhofer holograms, etc. A brief account of different types of holograms is presented below. Fresnel hologram. If the recording plane exists in the region where the diffracted field from the illuminated object is considered to be in the Fresnel zone, then the recording of the hologram is called Fresnel hologram. Fraunhofer hologram. If the recording plane exists in the region where the diffracted field from the illuminated object is considered to be in the Fraunhofer zone, then the recording of the hologram is called Fraunhofer hologram. Image plane hologram. If the recording plane is such that it receives an image, so consider here an image. If the recording plane is such that it receives an image of a three-dimensional object illuminated in the presence of a mutually coherent reference beam, then the recording of the hologram is called image plane hologram. If the three-dimensional object is lying in the vicinity of the recording plane, it may not be possible to bring all the parts of the illuminated object in perfect focus. Thus, some parts of the object will be well focused while the others will be defocused. Fourier transform hologram. In this type, the object of which the hologram is to be recorded is in the form of a two-dimensional transparency placed in the front focal plane of a convex lens, and the recording plane exists at the back focal plane of the lens. The object plane, the lens plane, and the recording plane all pierce the common optical axis normally. The object is illuminated by plane waves and its Fourier transform is projected at the recording plane where a reference beam at some angle is added as shown in the diagram. This is caption. Setup for a recording Fourier transform hologram. You see that a beam from the laser hits the beam splitter where it is divided into two parts. One part of the beam goes towards the mirror M2, the other part goes towards the mirror M1. The beam towards the after reflection from the mirror M1 passes through the beam collimator, where the beam is collimated and also expanded in diameter. This beam illuminates an object transparency placed just after the lens, and another lens is placed in such a way that the optical transparency or the object transparency is located at the front focal plane of this lens, and this lens generates the Fourier transform of the light through the object transparency at its back focal plane where the photoglass is placed. So this lens which is close to the photoglass is actually the Fourier transform lens, which is at a distance f from the photoglass and is also at a distance f from the object transparency. Now the other part of the beam from the beam splitter which goes towards the mirror M2, the beam after reflection from the M2 also passes through beam collimator, where the diameter of the beam is not only expanded but also the beam is converted into parallel wavefronts. This beam, which we call the reference beam, also illuminates the photoglass at some angle. So the object beam, that is which is the Fourier transform projected onto the photoglass, and the reference beam from the mirror M2 interfere together and form a hologram which we call the Fourier transform hologram, because the object beam is in the form of a Fourier transform of the object transparency. The zeroth order frequency is much intense as compared with the higher frequencies, and the recording of all frequencies with the same amplitude transmittance is not possible, and this is in itself a big problem. In the reconstruction process, the developed hologram is placed at exactly the same location where it was recorded and is illuminated by the same reference wave, whereas the object beam is blocked from reaching the recording plane or the Fourier plane. So if we want to reconstruct, you see that when this photoglass is illuminated by the object beam and the reference beam, then of course after developing this photoglass and after developing and drying and bleaching etc., this photoglass becomes the Fourier transform hologram. Now to reconstruct the object, this Fourier transform hologram is placed at its exact location where it was first illuminated, and the objective and the beam from the object is blocked because a beam blocker is placed after the lens after the object transparency. Then this Fourier transform hologram, which is placed at the place of the photoglass, is illuminated by the reference beam and the object can be reconstructed. So the Fourier transform of the object, which stores the information of the optical transparency or the object transparency, can be seen in the reconstruction process. Lensless Fourier transform hologram. Of course, as the name obvious, we are not using the lens to construct the Fourier transform. So let's read this paragraph. Typical arrangement for the recording of a lens Fourier transform hologram is shown in the figure. This figure. Setup for a recording lensless Fourier transform hologram. You see that a point source exists at the front focal plane of the lens L1. So it means that diverging wavefront are incident at L1 and the lens L1 generates plane wave after that towards the right. A part of the plane wave falls on the lens L2. The L2 focuses the beam from L1 and then makes a point source at its back focal plane. A pinhole aperture is placed over there in order to clean the beam, and this beam is then diverging out towards the recording plane. A part of the beam, only one ray of the reference beam is shown. So this becomes a reference beam because it contains no other information of the object contained in its path. So a spherically diverging wave is incident on the recording plane, which could be a photoglass in our case. A part of the plane wave from the lens L1 goes straight and is incident on the object plane where the object is placed. The light passing through the object reaches towards the recording plane. You see that we have shown a point source from which the reference beam is generated. And then you know that each point of the object acts as a point source. So each point of the object acts as a point source, so there will be an interference between the reference beam generated from the point source after the lens L2 and the point source at the object plane. So a point source at the object plane will also generate a spherically diverging wavefront towards the recording plane. So the beam from these two point sources, that is a point source after the lens L2 and the point source located at the object plane, will interfere at the recording plane. But you know that this object plane, which is consisting of apparently in the form of a mesh, for example, as shown in the figure, contains an infinite number of object points. So all these object points contribute at all points on the recording plane. So the reference beam will interfere with each of the contribution from these object planes, from these point objects located at the object plane. So an interferogram is recorded. So you see that here we can say that the beam, since we are considering in this case the model that the object plane consists of a large number of object points, and a single object point will contribute a spherically diverging wavefront at the recording plane. So you see that this is then becomes the Fourier transform of this point object located over here. And you know, since we are not using any lens after the object, so this is referred to as the lensless Fourier transform hologram. Okay, Fourier transform of the object transparency is not recorded in this arrangement. Spherically diverging waves from a point on the object. Consider that we are talking about a point on the object, and from the point reference source interfere at the recording plane and the corresponding fringe pattern is recorded. The fringe pattern may be considered as the Fourier transform, within bracket we have lengthless Fourier transform of the 2 point sources, one on the object and the other as the reference point source. N interferograms due to n point objects are overlapped at the recording plane. In the reconstruction process, identical reconstructing wave could be used, or equivalently, if a plane wave is used as the reconstructing wave, then the field after the hologram should be Fourier transformed. Object should be in the form of a 2-dimensional amplitude transparency. Reflection or white light hologram. In the recording process of reflection hologram, the object of which the hologram is to be constructed is placed behind the photographic plate and is illuminated through the photographic plate as shown in the figure. For example, this figure, in which we have a photo glass, and the emulsion side is facing towards the 3D object. The object is just placed very close or just touching the photo glass or the photographic emulsion, and then you know that this object is illuminated by a spherically diverging wave coming out from a point source. So this spherically diverging wave passes through the photoglass and then reaches the 3D object, from which the light from the 3D object is scattered out, and then of course a part of the beam from the 3D object reaches the emulsion. So there will be an interference between the light which is reaching directly onto the photoglass, which we may call a reference beam, and the beam contribution from the object which is scattered off the object and reaching the emulsion side, then that may be recorded as the object beam. So these two together interfere at the photoglass, and then of course the interferogram is recorded. So this is the setup for the recording of the reflection hologram. The beam that illuminates the photographic plate is the reference wave, while the beam scattered off the object and reaching the plane is the object beam. The two beams interfere at the recording plane and form a standing interference pattern. The angle theta between the two beams is nearly 180 degrees. The spatial frequency of the fringes formed just in front of the photographic plate may be found from the following expression. So you see that here we have said that there is an angle of 90 degrees between the reference beam and the object beam. Look at this condition. So only the light which is scattered directly back towards the point source from the object and the reference beam, then these two beams will make an angle of 180 degrees with respect to each other. But you know that the light from the object which is scattered towards the photoglass is not only the beam traveling towards the point source, but it is scattered in all directions, so making different angles. So different beams from different parts of this 3D objects illuminate the emulsion, illuminate the photoglass at different angles. So the maximum angle that we may talk about is 180 degree, where the beam from the 3D object is reflected straight back towards the point source. Only that part of the beam from the 3D object will make an angle of 180 degree. But for the other parts of the beam which are scattered in different directions and hitting the photographic emulsion at different points will be making different angle. So theta will be different in that case. So we may consider the extreme angle theta, because we want to see that what is the maximum value of the spatial frequency formed at the photographic plate. So for that one we are using equation number 34 to give the spatial frequency of the fringes, which is sine theta over lambda. So rather than using sine theta equal to theta here equal to 180 degree, what we do is that we make this sine theta is equal to theta by 2, and let's multiply it with 2. because here so that we can compensate the half angle that we are using with as an argument of sine theta. So here we can use the value of theta is equal to 180 degree, that is pi, and then you know that pi by 2 is equal to 90 degree and sine of 90 degree is 1. So we have 2 over lambda. You can divide 2 to the lambda and we have 1 over lambda by 2. In the denominator, you can set the denominator equal to lambda by 2, which could be the spatial period for the fringes that are formed on the photoglass. So we have the spatial frequency which is equal to 1 over the spatial period, and this spatial period is over here is equal to lambda by 2 as given in equation number 34. And you know that here we have used the maximum value of theta to be 180 degree, but you know that theta could be any value going from maybe slightly greater than 0 value to the maximum value of 180 degree, because of the scattered light from the 3D object hitting the photographic glass at different angles. The fringes so formed in the hologram are parallel to the plane of the plate and bisect the angle between the object and the reference beams. So you see that let's consider any angle theta other than 180 degree. So when the reference beam and the object beam interfere at any angle theta, the fringes are so formed that they bisect the angle between the object beam and the reference beam. The fringes have been shown in the hologram in the reconstruction process shown in the next slide. For example, this one. You can see that the light scattered from the object is going in different directions. And also you can see that the fringe pattern is shown over here. That is scattered of the hologram. But I shall come it later. Let's read complete the paragraph. The reflection hologram is also known as white light hologram because a white light source can be used to reconstruct the virtual image seen through the hologram. When a white light source is used to illuminate the reflection hologram, the wavelength that satisfies the Bragg condition will be reflected off the hologram, whereas the other will be transmitted through the hologram. The others which do not satisfy the Bragg condition will be transmitted through the hologram, and the beam which will satisfy, or the wavelength that will satisfy the Bragg condition will be reflected off the hologram. So this is the setup for the reconstruction of the reflection hologram. You see that here the object is the 3D virtual object which we have shown is constructed behind the hologram, and we are illuminating the hologram by the incident white light from the left. The white light is traveling from the left and is illuminating the hologram from the left, whereas the object is reconstructed at the back of the hologram, because this is the 3D virtual image of the object. And you know that from this virtual object it appears that if the light is scattered out in front of the hologram, and this virtual object can be seen from the back of the hologram while looking through the hologram. That is, while looking through the virtual image through the hologram. If the same monochromatic light identical to the one used in the construction process is used to illuminate the object, the hologram may not be able to reconstruct the image due to the failure of a Bragg condition. It is because emulsion during the hologram development process may shrink and requires a shorter wavelength for its reconstruction. This is why a white light source is used in the reconstruction process. Reflection holography is an addition to the display holography and is safe because of the use of the white light in the reconstruction process. A rainbow hologram. A reflection hologram can be constructed with white light, and the hologram selects one wavelength which satisfies the Bragg condition. Transmission type holograms are reconstructed with the same monochromatic wavelength used in the recording process. But if the transmission type holograms are reconstructed with white light, the reconstructed images will smear out due to chromatic aberration, due to chromatic dispersion. Images with chromatic dispersion may be interpreted as if a large number of reconstructed images slightly shifted slightly shifted spatially and produced under different monochromatic waves are added to give a resultant smeared out images. So you see that if we are using a white light to reconstruct an image through a transmission hologram, then you know that since violet contains a large number of wavelengths, so each wavelength would construct an image, and then you know that we shall have so each reconstructed image will be slightly shifted spatially, that is slightly shifted in space due to different wavelengths and produced under different monochromatic waves. These images which are produced under different monochromatic waves are added to give a resultant smeared out image. So the resultant image will be smeared out because of the addition of many reconstructed objects, many reconstructed virtual objects. A virtual image obtained from a transmission type hologram has a two-dimensional parallax. This two-dimensional parallax is maintained during the construction process, and as a result of the reconstructed images also appear in full two-dimensional parallax. In a transmission type hologram, if parallax in one dimension is allowed and parallax in the second dimension is blocked during the hologram construction process, then the blur in the reconstructed images due to the chromatic dispersion can be avoided. So you see that the chromatic dispersion and the smearing out of the reconstructed image, as mentioned in the reconstruction of the white light hologram, in the construction of the transmission hologram with white light, can be avoided during the construction of the rainbow hologram, where during the hologram construction the process and the parallax in the second dimension is blocked during the hologram construction process. Then the blur in the reconstructed images due to chromatic dispersion can be avoided. So you see that we shall block the parallax in one dimensional and allow the parallax in the other dimension to contribute in the formation of the hologram construction, and then the chromatic dispersion can be avoided, and so no smearing out of the object can be seen when we are talking about in respect of the rainbow hologram. The recording of a hologram with only one parallax may be regarded as a rainbow hologram. So look at the definition that we are using. Recording of a hologram with only one parallax may be regarded as rainbow hologram. Construction of a rainbow hologram involves two holograms recording. The first hologram is recorded of a given three-dimensional object using the setup shown in the figure. A spatially coherent monochromatic beam is used to illuminate the 3D object, and a mutually coherent spherically diverging beam. When we say mutually coherent beam, it means that the beam is generated from the same source. And a mutually coherent spherically diverging beam, which we call as the reference beam, is used to illuminate the photographic plate directly. The scattered beam from the object interferes with the reference beam at the recording plane, and the resultant interferogram is recorded. So look at the setup. Since in the rainbow hologram we are recording two holograms, so this is the setup for the recording of the first hologram. So you see that let's talk about the monochromatic illumination from the spherically diverging wavefront. So there is a point source at the top which we have not shown, and the light from the point source is diverging spherically out and illuminating the 3D object. So the light scattered from the 3D object contributes at the photoglass. So this diverging beam also hit a scatterer, a point scatterer which we have placed close to the object. The diverging beam from the monochromatic source also illuminate this point scatterer, and the light from this point scatterer also diverge out in the form of spherically diverging wave and contribute at the photoglass. So two beams, one is the beam from the 3D object scattered off towards the photo glass, and the other beam from the point scatterer or the point reflector contributes spherically diverging wave at the photo glass. So these two beams, that is the object beam and this reference beam, interfere together and form an interferogram which is recorded on the photo glass. and the photoglass after the exposure is developed and is fixed, and then is dried, and then that becomes and then the photoglass turns out to be a first hologram, and this is the first hologram, which is the transmission hologram. Setup 1 in the rainbow hologram recording. Setup for the construction of transmission type hologram of a given 3D object. So you see that this scheme is just the scheme that we usually use as for the construction of the hologram using transmission hologram. So this is the transmission hologram because we have the two beams, one from the object and the other from the point scatter. Both are contributing from the same side towards the photographic towards the photoglass, forming an interferogram, and then of course this is the setup that we call as a transmission type hologram. So you see that in this first hologram is recorded in connection with the rainbow hologram. Now we have to record the second hologram. Let's see how that is done. The hologram is developed and is placed in the setup shown in the figure, where a second hologram, that is the rainbow hologram, is recorded. So the recording of the second hologram on the transmission hologram is called the rainbow hologram. So what we are doing over here? So let me explain this diagram first. Let me first of all read the caption. Step 2 in the rainbow hologram recording. Second hologram recording with the object beam generated by the first hologram after forming a real image through the horizontal slit. So look at the point source. The real point source, that is a point source from a laser source, which is illuminating, which is diverging spherically outward towards the positive lens. And then you know that this lens is illuminating the hologram 1, which we have just constructed using the previous setup. And you can see a slit also just before the hologram. So it means that this hologram is being illuminated with a slit also. So this diverging wavefront, after passing through the positive lens and after passing through the slit, illuminates the hologram 1. And then you know that the light from the hologram, you see that this point source which we are using is actually a conjugate of the spherical wave. You know that when this diverging spherical wave from the point source passing through the positive lens, this lens will focus this point source, and then you know that you can see that a focus points on the left hand side of the hologram, which we call as spherically converging wavefronts. These spherical converging wavefronts, after passing through the hologram, which are undiffracted beam, is focusing over here. And you know that in the construction of this point, this is the real point source, but you know that here this is also a real point source, but we are illuminating the hologram with a reference, with a conjugate reference beam using the point source over here. And the light which is undiffracted through the hologram is also being focused at some point after the hologram. But you know that when the hologram is illuminated through a light from this point source using a slit, then of course since we are using a conjugate reference beam, it means that the hologram will generate a real image. So it means that the light after the hologram will converge and form the real image. So the light from this real image contributes towards the photoglass. It means that a real image is also recorded at the photoglass, at the plane of the photoglass. But you know that we are using another point source which is coherent, that is this point source on the right hand side in the bottom figure, and the point source which is above in the part of the figure which is above is also generated coherently, that is both from the same point source, from the same laser. So it also generates spherically diverging wave passing through the positive lens given on the top figure, and then you know that this positive lens converge the beam at the point, and you have spherically converging wavefronts which are also being focused after the photoglass. And the photoglass is illuminated with a spherically converging wavefront. So there are two beams which are reaching the photoglass. One is the reference beam, which is coming out from the point source from the above setup, and the real image which is given off by the hologram 1 using the lower setup. So the real image from the hologram and the reference beam from the upper setup both contribute at the photoglass, and then the second hologram is recorded. So this recording of the second hologram, that is the exposure of the photoglass, which is developed and then fixed and then dried, then it turns out to be a second hologram. So this second hologram is called the rainbow hologram. So remember that we are using a slit over here. This is important, By using a slit, we are restricting the two-dimensional parallax to one-dimensional parallax. A horizontal slit is placed just after the hologram, and the hologram is illuminated with a conjugate reference beam. The slit blocks the vertical parallax. The real image of the 3D object is formed due to the converging beam generated by the hologram, which propagates further and illuminates the photographic plate. A mutually coherent point source is used to generate spherically diverging beam to illuminate the photographic plate directly, acting as the reference beam. The two beams interfere at the recording plane and the resultant interferogram is recorded. The developed hologram is then known as the rainbow hologram. To reconstruct the real image from the rainbow hologram, it is illuminated with a conjugate reference beam, as shown in the figure below. Further, beyond the real image, an image of the slit is also formed at the same location where it is originally existed. So you see that once we have constructed the second hologram, that is the rainbow hologram, we shall try to extract the real image from the rainbow hologram. Since you know that in order to reconstruct the real image, we have to illuminate the second hologram with the beam which is conjugate of the reference beam we are using over here. So let's show the second setup for the reconstruction process. So you see that now over beam, you see that here the beam is focusing where we have labeled it spherically converging wavefronts. Now we shall place a source, a light source over here that will diverge out. That is the beam will travel backward towards the point source which is shown at the top. And the direction of the illuminating beam will be reversed. That is the reverse of the reference beam used in the construction process, which we call as the conjugate reference beam. So here in this setup we are showing the conjugate reference beam. This is illuminating the hologram 2, that is the rainbow hologram. And you know that from this rainbow holograms we are using the conjugate reference beam. A real image is formed at its location. We have placed the hologram in the setup where it was used for the construction process. You see that instead of a photographic glass, now we have the hologram number 2 over here. And then we have the real source over here, which is diverging out. So this real source is actually giving you the conjugate reference beam with which the hologram 2 is illuminated, and then of course the hologram will produce a real image at the location where the real image was formed in the above setup. And you know that when the light will further travel after forming the real image, then of course the image slit will also be formed. And this is also the real image of the slit, because you know that the slit over here is just behind the hologram. So first hologram I mean. So you see that this is again the image of the real image of the slit is also formed. So this is the reconstruction of the rainbow hologram. Image is viewed through the slit. So you see that if you want to see this real image, then you need to look through this image slit, through the slit of this image. So you will look through the slit, and then you will be able to see the real image of the real image stored in the rainbow hologram or the hologram number 2. With monochromatic reconstruction, a single real image of the object and a single real image of the slit are formed. With white light reconstruction, multiple real images and multiple slit images are formed, and through each slit, a real image with a unique color is viewable, eliminating the problem of image blur. due to the chromatic dispersion. If the real image is viewed through different slits by moving head up and down, real images with different colors can be seen, justifying the name rainbow hologram. The size of the real images also varies from slit to slit. The rainbow hologram falls in the category of display hologram, as the reconstruction of the images with white light is possible. Now let's talk about the multiplex hologram. It falls in the category of display holography because of the reconstruction of the hologram with white light source. Multiplex hologram is usually presented in cylindrical format, which is its most popular version. To record a multiplex hologram, a large number of photographic negatives of a given scene recorded with different perspectives are first prepared. The object is mounted on a precision rotating table as shown in the figure below. The table is rotated in small angular steps. For example, 1/5 of a degree is typical with respect to the photographic camera, and in each step the object is recorded. So you see that the object is mounted on a rotating table and the table is rotated very precisely, for example to the 1/5 of a degree, and then you know that in each new perspective the camera takes an image of the object, and then you know that a large number of objects are stored in the camera in different frames. So different negative transparencies of this object can be recorded using this setup. And you know that all perspective of this object, since the object is rotated through 360 degrees, so all aspects of this object are recorded. So this is the setup for the preparation of negative transparencies of the object with the different perspectives due to object rotation. For complete object rotation cycle 1800, which means that 360 multiplied by 5 frames are recorded. The negatives are developed and each of which act as an object transparency for the multiplex hologram. These negative transparencies are projected one by one coherently onto a cylindrical lens L2, which focuses them as the vertical line image on the photographic film as shown. So let me read. A mutually coherent beam in the form of line focus is added where the line image is focused. So let me explain this diagram. This is a setup for recording of a multiplex hologram. You have a point source 1 which illuminates the lens L1 with a spherically diverging beam, and the lens L1 convert that spherically diverging beam into plane waves, and these plane waves passes through the photographic negative which we have prepared using this setup. So these photographic negative in the form of a film roll are passed one negative at a one time, and so one negative is illuminated at one time, and the light after each of these negative transparency is passed on towards the mirror towards the cylindrical lens L2. This cylindrical lens L2 generates a line image of this object transparency at the film roll shown on the right side of this in the form of a line image. So a line image is created by the lens L2, which is a cylindrical lens. That's why you see that we have shown very much line strips on the film roll on the right hand side. So for each negative transparency, when a next negative transparency is moved, similarly this film roll is moved to the next position, so that the exposure is done on another blank region of the film. Then you know that notice that there is another point source 2 which generates spherically diverging beams, and you know that we also place a slit over here which we have not shown in the setup. That slit is arranged in such a way that a vertical reference beam is projected onto the film roll at the same position where the line object of the negative transparencies generated by the L2 focus are focused. So that there is an interference between the reference line image, between the reference line beam and the reference of and the line object beam. So these two beams interfere, and for each negative transparency, for the next transparency of negative transparency, the film is also moved, the film roll in the above setup is also moved one step further, so that there will be a recording of the corresponding negative transparency in the next position. A reference beam is generated from a mutually coherent point source. Mutually coherent point source means that is generated from the same laser source from which the point source 1 is generated. So point source 1 and point source 2 are the mutually coherent sources generated from the same laser source. The reference beam is generated from a mutually coherent point source lying vertically above the cylindrical lens L2 and is directed towards the photographic plate after passing through the slit, which is not shown, where it forms a vertical line overlapped on the vertical line image of the object transparency generated by the cylindrical lens L2. The film at the recording plane is moved one step forward when a new object slide, that is the frame, appears at the object plane. When the film has been exposed with all the object slide images in the presence of the reference beam, then the film is developed, resulting into a multiplex hologram. To reconstruct these stored images, the hologram is folded in cylindrical shape and is fixed on a rotating table. The base of the table contains a white light source with vertical filament, so that the white light reaching the film nearly resembles to the conjugate of the original reference beam. So you see that here we are using the word resembles to the conjugate of the original reference beam used in the construction process. So you see that here the reference beam that we have used over here in this setup, we are generating the conjugate of this reference beam by the arrangement that just we have described over here. The deviation of the white light from being the conjugate of the original reference beam results in blurriness in the reconstructed images. Dispersion occurs at the hologram with the red spectrum shifted vertically downward and the blue spectrum shifted vertically upward. The reconstructed images are viewed through the hologram, and two eyes of an observer focus to different perspective of the same object, and thus due to the stereo effect the reconstructed images appear three-dimensional. The rotating table can be rotated to view all possible perspectives of the stored images. The preparation of the negatives using the setup shown earlier does not allow vertical parallax to appear. Thus, vertical parallax does not appear in the reconstructed images generated by the multiplex hologram. So this is the setup for the reconstruction setup. So you see that we have the same roll on which we have recorded each hologram, and then you know that this is the developed hologram that we have placed, and through this hologram the object is visible under the illumination of light of the white light source, which is located in the center of this hologram, of this cylindrical molded hologram. So white light source with vertical filament as a reconstructing source, generating reference beam. But generating which reference beam? It is actually generating the reference beam conjugate of the original reference beam. So you see that multiplex hologram folded in cylindrical shape, rotating table, white light source with vertical filament as a reconstructing source, and this is the multiplex hologram in a cylindrical form and the reconstructed images with white light. So reconstructed image will appear within the cylindrical region of the hologram, exactly at the same position where it was placed in the recording process. For example, over here. So it will appear at the same position. But you know that we are looking at that one through the hologram, and you know that this will form a real image of this object. because we are using a conjugated reference beam in order to reconstruct the hologram. Now, stereo hologram. These are generally known as the holographic stereograms. In stereo hologram recording, first the object negatives are prepared with a different perspective. For example, horizontal perspective using the setup shown in the figure below, where the object is fixed and the camera is translated horizontally between successive recordings. Look at this one. This camera with horizontal translation arrangement is placed on this table. And you know that this arrow on the stand, that is the two-dimensional arrow, indicates that the camera can be moved horizontally towards the right and towards left, whereas the object is fixed over here on a fixed platform. And this is the recording setup of the object negatives with a different horizontal perspective. The negatives are developed and then illuminated coherently with plane waves which are focused by a positive lens L2 onto the ground glass as shown in the figure on the next page. So let me show the reconstruction. This is the recording setup of the stereo hologram. You can see this is the point source 1, illuminating the lens L1 with a spherically diverging wavefront, and the lens L1 will generate plane waves which will illuminate the object transparencies, and after the object transparencies the light will be received by the lens L2. And there is a ground glass as a diffuser just after the lens L2, and you know that the light from the diffuser will reach the photo glass, where we have placed a slit over here, and this slit is movable. You know that the white arrow indicates the direction in which this slit can be moved, and a point source 2 is there which generates the reference beam to record the hologram within the space provided by the slit. So this is the recording setup here. And you know that for each movement of this object at the object transparency, that is the transparencies at the object plane, for each movement only one object transparency is illuminated at a single time. So when the next transparencies comes at the position of the object plane, then you know that this slit is also moved one step towards left or right depending upon the direction of the object transparencies which are placed, which are moved using the film roll. So the same slit, slit is also moved on the left side or on the right side. But you know that here we have shown that the slit is being moved towards the left because we have also indicated an arrow close to the left hand roll where it indicates the movement of the film. Ground glass acts as a scatterer, and the optical signal at each point of the ground glass is spread over the recording plane. That's why we have placed the ground glass there. A mutually coherent reference beam is mixed from the side. When the next transparency is illuminated, the slit is moved horizontally in the same direction. Interference occurs between the reference beam and the beam from the diffuser. The slit displacement between the successive recordings is such that the two consecutive interferograms partially overlap. That is, the holographic exposures of the negative transparencies are made side by side. After completion of exposures, the photographic plate is developed and the stereo hologram will be ready to use for reconstruction. The reconstruction setup is shown in the figure. For example, in this figure. I shall come back to this figure after reading this paragraph. The stereo hologram is illuminated by an identical reference beam. You can see that we have placed the hologram at exactly the same position, which is now the stereo hologram, and the reference and the point source which generates the reference beam is located at the same position and illuminating the reference and illuminating the stereo hologram from the same position. And you know that the observer is on the other side of the hologram, looking through the hologram and looking at the virtual image through the hologram. So these are the two eyes of an observer which are looking through the stereo hologram and look at the virtual image. So two different aspects of the virtual image can be seen by the observer. So this is the reconstruction of the virtual image from a stereogram. The reconstruction setup is shown in the figure. The stereo hologram is illuminated by an identical reference beam. The observer can view the virtual image through the hologram. The two eyes of the observer view two different perspective of the virtual image, and through stereo effect view the image appear as three-dimensional. Only horizontal perspective of the image is preserved and the vertical parallax is completely blocked. It is because in the recording of negative transparencies only the horizontal parallax was allowed and the vertical parallax was blocked. A brief description of holography, its different types and mathematical representations of hologram recording and reconstruction were presented in this course. The knowledge about the holography has extended so much that volumes of books can be written on the subject. Holography, being a part of the Fourier optics curriculum, has been included and discussed. I hope that the readers will find the given information relevant and useful. So, end of basic course on Fourier optics. So you see that this is the last slide. That is the slide number 73 is the last slide of this course. So that's why I have the title, End of Basic Course on Fourier Optics. Total number of slides that cover the essential components of a basic course on Fourier optics is 73, and each slide roughly covers an average number of pages above 10. That is roughly nearly 800 pages. So you see that I hope that the number is well above 800 pages. Slides are freely available for everyone to download, read, consult, suggest to others, etc. I have created it for the betterment of humanity. Those who follow the contents of this course from slide number 1 to last slide would be able to carry out research in the field of optics and can design any optical system. A real designer, in addition to this course, would require another course on computational Fourier optics. If I would remain healthy and life permits, I might be able to work on the computational Fourier optics course and would present it free to the humanity. I do not want anything in return but good wishes. So enjoy the stuff. Well-wisher of the humanity. I myself, Asloob Ahmad Mudassar. So this is the end of slide number 73 and at the same time the end of the course on Fourier optics. Good luck.